In this video, we're going to do a review of the Bohr model itself. This is a model of the atom that you should have learned about earlier in your scientific education career, and it's something we need to kind of refresh a little bit so you can understand how it's used in later discussions in this unit. Just a quick list of learning objectives to go along with this discussion. First, we'll talk about what the Bohr model is itself, a very general overview. We'll then talk about the scientist responsible for creating it, a fellow by the name of Niels Bohr. We'll then talk about the actual usage and application of the model, get into some of the more detail, and finally, and probably most importantly, we'll end with a discussion on things called electron configurations. Every model of the atom creates what's known as an electron configuration, and that configuration is really the working component, things we actually use in the daily application of chemistry in order to understand the atom better. The better your model, the better configuration you can get. The Bohr model is the first chance we get to work with an electron configuration, so we'll hopefully put some together before the day is done. So to begin with, we'll talk about what the Bohr model is itself. Well, it's basically a model of the atom that arranges electrons into concentric rings around the nucleus. And this is really the key term here, is this concentric rings. We're going to have a diagram of that Bohr model in front of us in a second, and it's going to look familiar. A lot of times, because of those concentric rings, this is referred to as the planetary orbit model. Bohr originally made his assumption about electron movement based on the fact that planets orbit around a sun due to the attractive force of gravity, and he basically theorized then that electrons should orbit around a nucleus because of the electromagnetic pull. They're different forces, but they're acting in the same way, and he expected similar results. This model then was put together based on observations made by a bunch of different scientists, ending with Bohr, not necessarily starting with him. J.J. Thomson was the first person to start finding subatomic particles. He discovered the electron itself, and that's how Bohr was able to put electrons into his model. The model was refined again by a fellow by the name of Ernest Rutherford, who took Thomson's very rudimentary model and made the orbiting, the dense nucleus and the electrons surrounding it. And then finally, all this was pieced together with the discoveries by Bohr himself to create the current model. We've already spent some time talking about the other scientists involved in this process. Let's take a moment now and talk about Bohr in a little bit more detail. So Niels Bohr was born in October 1885. He is remembered as a Danish physicist, and we've talked a couple times in this chapter about a lot of this falls under the category of physics and not chemists, although chemists take a lot of advantage of these discoveries. Bohr's work allowed him to receive a Nobel Prize back in 1922. He's basically credited with the discovery of the idea of quantum mechanics and also a foundation for a lot of what we know today about atomic structure, and that's what he received his Nobel Prize for. Other notable things about Niels Bohr: he was one of the scientists selected to be on the Manhattan Project. For those of you a little rusty with your history, the Manhattan Project was the project in the U.S. to develop the atomic bomb. Bohr actually was a big activist over in Europe during World War II before he left the area, trying to kind of mobilize scientists and other people to fight against the Nazis. He was then brought over to the U.S. and continued that struggle by being involved in the Manhattan Project. After the war, he was associated with one of the scientists who developed the research facility CERN, which is currently one of the leading research facilities in Europe today. And finally, another great credit for him is the fact that many of his students and his teachers went on to receive Nobel Prizes as well. You know, you can imagine this was a whole bunch of guys that would sit down and have coffee together, and each one of them had a Nobel Prize to each of their names. So this was a very significant group of scientific individuals. So let's get back then to the model that Bohr created and provide a little bit more of the detail so we can actually use it to do something a little more scientific. So first of all, as we mentioned before, electrons orbit the nucleus in concentric orbits or concentric rings. And these orbits have a couple different names depending on who you talk to. They can be referred to as rings, shells, or orbits. I believe the official technical right term is the idea of shells. But again, these names are used interchangeably. As we already mentioned, it's similar to how planets orbit our sun. These electrons then are held in place by electromagnetic forces. If you recall from earlier in the year, the electron itself has a negative charge. The nucleus overall has a positive charge. And due to Coulomb's law, there is an electromagnetic pull on these electrons towards the center and towards the nucleus. And that's what holds them in orbit, similar to the way that gravity holds planets in orbits as they go around our sun. Each of these rings then represents a place where electrons can orbit this nucleus, much like we have planets orbiting in different rings. And each of these rings has a maximum number of electrons that can actually hold. And we'll talk about that more in a second. When we place electrons in this model, they're always placed in the lowest available ring first, and then we move towards the outside as those maximum numbers are reached. And then finally, as I already said, when one ring is filled, we move on. The next electron is placed in the next lowest available ring. So this then brings us to the idea of electron configurations itself. We want to take those basic ideas that we just talked about the Bohr model and use them as a tool to actually place electrons in the model itself. And again, the goal with an electron configuration is going to show us or predict for us the chemical behavior of that substance based on how the electrons are arranged. So as we already said, electron configurations are a depiction of the arrangement of electrons in an atom. They determine the chemical properties of that atom. So because of the way the electrons are arranged, that's going to determine what type of chemistry that atom can be involved with. Finally, and we talked about this very briefly in the beginning, the quality of the model that your configuration is made with determines the quality of the predictions that you can make. The Bohr model is one of the better models to come along in its time, but it isn't the best model we have today. As a result, it can make certain chemical predictions about an atom, but there are other predictions it cannot make. We need a better, more refined model to understand that level of chemistry. And as new models come along, that'll refine our understanding of those chemical properties even further. So let's talk about the rules then for making electron configurations with Bohr. You're going to notice a lot of the ideas we talk about now are very similar to what we talked about in the actual description, but now we're going to put them in more of a procedural kind of way. First of all, you need to know the number of electrons that are being placed in your actual model. If you recall from earlier in the year, we had an equation associated with electrons, and that's this guy right here. Charge is equal to number of protons minus number of electrons. You can use this equation then to solve for a quantity of electrons given the charge and the number of protons. You're always going to, once you figure out those number of electrons, you're going to start by placing electrons in the lowest available energy level. Lowest available energy level is always going to be the innermost ring. And when that ring is full, that forces us to move on to the next one. So when the lowest energy levels are full, you place electrons in the next lowest available energy level, which is the next lowest ring. You'll basically then continue this process until all the electrons that you counted up from earlier, from up here, have ultimately been placed in your model. Now, we mentioned the fact that each ring has a maximum number of electrons. We talked about when it's full. We need to define what those numbers are. How do you know when ring 1 is full? How do you know when ring 2 is full? That's where we're heading next. So here what I've done is shown a kind of cutaway diagram of the actual atom. Each one of these arcs represents one of the rings that our electrons can reside in. Generally speaking, these rings are numbered. The symbol we use for each ring is the letter N, and then it's got a number that goes along with it. Ring 1, 2, 3, 4, 5, 6, and 7. 7 is the maximum number of rings needed to hold all electrons in even the largest atoms. However, there are hypothetically rings beyond that as more atoms are discovered and as electrons get promoted to higher energy levels via spectroscopy processes. Anyway, the goal of this slide, though, is to talk about the maximum number of electrons that can reside in each ring. So really quickly, we can go over here. Ring number 1 is one people often remember, holds 2 electrons. Ring number 2 holds 8 electrons. These are numbers people usually remember. It's ring 3 where people start having trouble. Ring 3 also holds 8 electrons. Ring 4 holds 18. Ring 5 holds 18. And then ring 6 and 7 hold 32 electrons each. So these numbers are very important to remember because, again, it gives us an idea of these capacities. I'm going to put my first 2 electrons in ring 1, then I know it's full. Then I'm going to start placing electrons in ring 2 till it's full, etc., 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 until you've placed your maximum number of electrons. Now, you might be saying to yourself, ugh, that is a difficult number to try and remember. I don't want to have to worry about those. The reality is you don't have to have those numbers memorized. Our periodic table of elements actually gives us that answer for us. The way this works, we can think about the row numbers that go along on our periodic table. There are 1, 2, 3, 4, 5, 6, and 7 rows to worry about on our periodic table, and each row has a certain number of atoms in it. The first row on the periodic table, so let's make a little table over here. The first row in our periodic table has 2 atoms on it, and if you think about the first ring in the atom, it holds 2 electrons. The second row holds 1, 2, 3, 4, 5, 6, 7, 8 atoms, and the second ring holds 8 electrons. We can start seeing a pattern develop here. If you count the third row, it has 8 atoms. The third ring holds 8 electrons. The fourth row has 18 atoms. You can take the time and count all the way across from these. That fourth ring holds 18 electrons. We get 18 again here and another 18 electrons. And then rows 6 and 7 each have 32 atoms. And that's because it includes these elements here, then all of the elements down at the bottom, and then we continue the process counting. And again, if you were to count all those up, it adds up to 32. And that again matches the 32 electrons that go in each ring. So basically what you can take away from this is that if you need to know how many electrons are in ring 3, you just need to know how many atoms are in row 3 on your periodic table. Those numbers always match. This, of course, is not a coincidence. The periodic table was made in this fashion in order to show these kinds of patterns, and as we talk about the periodic table a little bit later in the year, you'll start to understand more about why these patterns actually exist. But for now, this is simply a neat trick you can use for remembering the maximum capacities for electrons in each ring. So to wrap things up then today, let's talk about a really quick example. We can draw a Bohr model for the element sodium. To start with, we're going to need an atom to work with. In this case, I know my sodium atom is only going to need 3 rings to work with. Notice I didn't draw the whole rings in here. I can just draw these crescents. It saves you a little bit of time. First things first, we want to figure out the number of electrons we're dealing with. Let's assume this is a sodium atom with a charge of 0. That means that charge 0 is going to be equal to the number of protons, which is 11 from our periodic table, minus some number of electrons. Well, clearly in this case, our number of electrons must equal 11. Now, if you want to figure out how many rings you're going to work with, 11 electrons will tell you that. We can get 2 and 8 in the first 2 rings. That gets us to 10. One more would get us our 11. But you'll also notice on your periodic table that sodium is in the 3rd row. And if it's in the 3rd row, as we kind of already alluded to, it's going to require 3 rings. Once you figure out the exact number of rings, you can actually start placing them. 2 electrons go in the first ring. That is max. That ring's now full. We can then place 8 more electrons in the second ring. That gets it to full. That gets us to 10. And then finally, we can place 1 more electron in the last ring, the 3rd ring here, to get us to a total of 11. When you start drawing in the ease is fine. Later on, you'll find you can actually just label these with numbers to show how many electrons are in each ring as well. Putting the model together is relatively straightforward, but again, the point of this process is to predict the behavior of the atom afterwards. In later chapters, we're going to take very important note of the fact that this ring only has 1 electron in it. And as we will learn, atoms prefer to have shells that are completely filled. This one's completely filled, and this one's completely filled. You can imagine that the atom looks at this lone electron here in a very unfavorable light. It would like to get rid of it. That being said, we would expect this atom to lose this electron in a chemical reaction, and because it's so close to having this perfect configuration, we would expect it to do that very violently. Now, as you can see from the video showing now, this is an example of putting sodium metal into water. As you can see, it catches on, it heats up very quickly, it gives off a lot of smoke and fizzes, eventually catches on fire, and if there were a large enough supply here, we would actually see the sodium explode. The important thing to note is we're seeing the violent chemical behavior and the loss of the electron that we were able to predict from the actual model itself. And that's the purpose of these atomic models. To conclude for the day, again, a list of things that you should be able to do. You should be able to explain the basic characteristics of the Bohr model of the atom, what are its basic layouts, and then finally, you should be able to build an electron configuration of a Bohr model using the rules we talked about. In later chapters, we'll develop this further and talk about more about what you can do with the Bohr model as opposed to just the configurations we create.